this is APAB. We're still doing 2.3 higher order derivatives. So we're going to walk through an E7 and a P7 just to show you how higher order differentiation works. And then we'll do some other trick problems, and we're going to talk a little bit about that acceleration and velocity and position stuff that we've talked about before, which is particle motion. So for E7, I give you an f of x that's a nice, happy polynomial, right? F of x equals 4x to the fifth minus 3x squared plus 8. And I've asked you to find f triple prime of x, right? So that means the third derivative. So honestly, you're just going to go ahead and find all the derivatives on your way to get there, right? So f prime would be, if I differentiate the 4x to the fifth, I'm going to get 20x to the fourth minus this 3x squared is going to become a 6x, right? And the 8's going to differentiate to 0, right? Because it's a constant, so it's going to disappear. My f double prime is now going to be the derivative of that, which would be an 80x to the third minus a 6, right? My f triple prime, which is the thing I was asked to find, is going to be a 240x squared. Okay, so that's the first answer. Notice there's no good way to skip to the third derivative. You really just need to do all of them. And we'll talk about that. You can certainly find patterns in certain problems, but in general, that's the short answer. Now, in part B, I ask you to find the sixth derivative of f, which is f6 in the parentheses as a superscript, and then of x. And then I ask, how can this help you logic through finding the 25th derivative of f of x without actually differentiating 25 times? So I'm actually going to do the work for this guy up here because I already did the third derivative. So my fourth derivative of x, of f of x, is going to be a 480, right, times x. So 480 times x. And my fifth derivative is going to be just the 480. But now an interesting thing's going to happen. See how 480 is a constant? Well, when I differentiate a constant, which will be my sixth derivative, right, I'm going to get 0. And then since 0 is also a constant, what I can see from this is that every subsequent derivative, right, so for n greater than or equal to 6, starting at 6, the nth derivative is going to be 0 here because this was a constant. Now, that's not going to be true in every example we try. So, but in this case, with this polynomial, every polynomial eventually derives to 0. So the 25th derivative of this thing will also be 0. If I asked you for the millionth derivative of this thing, it would also be 0. So every polynomial eventually derives to 0 if you keep going. Now, that's not going to be true of every function we deal with. So I want you to try a P7. It's the same basic idea, but I give you a slightly different sorry, there's a light on top of that. I gave you a slightly different polynomial. So it is a negative 3x to the 6th plus 7x cubed. Pause me if you want to do it without me. I'm going to go ahead and walk through. So my f prime of x is a negative 18x to the 5th plus a 21x squared. My second derivative is going to be a negative 90x to the 4th plus a 42x. And my third derivative is going to be a negative 360x to the third plus a 42, right? So that's the answer to the first part. And then the same thing's going to happen here. If I want to derive all the way down to the seventh derivative, I'm going to end up with a 0, right? And I can do that work here. So the fourth derivative would be a, I don't feel like multiplying by 3. It's a 900 and that's a 180. So negative 1080 x to the second, right? And the 42 disappears. The fifth derivative, look at me picking big numbers, would be a negative 2160 with an x, right? The sixth derivative would just be the negative 2160, which means the seventh derivative would be the first one to hit 0, and then every subsequent derivative after. So now they're all going to be 0 because every time I differentiate a constant, I just get another 0, and so the 25th derivative, which is the one I specifically asked about, will also be 0, right? Cool. So let's go ahead and walk through some other examples. Okay, so for example 8, I'm going to give you y equals the sine of x, okay? And I'm going to suggest that we should find the fourth derivative, and so we'll call that a. And then I want us to find, so B my B, I want us to find, let's do the, Oh, here, let's use the other notation just so that you get used to it, right? Let's do the 7th derivative, right? And again, this is the same as saying a y with 7 primes or a y with that 7 in parentheses, right? Okay, and then for P8, right? So for P8, I'm going to give you a y equals, let's do a cosine of x. So for A, let's find the 5th derivative, and for B, let's do the 10th derivative, just for fun. All right, so now you might say, okay, wow, okay, you're making us differentiate 10 times or 7 times, that's a lot of times. I picked both of these because I want you to spot that there's a pattern. Okay, so let's start with this sine x problem. So my y, so I know y is sine of x, right? Which means my y prime, the derivative of sine, if I use that note card that I made to write down, the derivative of sine is cosine, right? The second derivative would be the derivative of cosine, right? So now I differentiate the function I just got, right? And the derivative of cosine is negative sine, right? The third derivative, right, would be the derivative of a negative in front of a sine. Well, sine differentiates to cosine. We already saw that. So this is going to be a negative cosine, right? Which means when I differentiate the fourth time, right, I'm going to get a negative in front of the derivative of cosine. Well, that's a negative in front of a negative sign, which is totally just a sign. So I want you to notice it's not an accident, and there's a reason very specifically that in this case I asked you for the fourth derivative. So I want you to notice that the fourth derivative of sine is also sine. So I started at sine. When I hit the fourth derivative, it's also sine. What that means is that this is a loop. This is just going to keep happening, right? This is a loop. Because if I start deriving, like if I differentiate again from here to get the 5th derivative, well, this is also the 5th derivative because I'm back at the start, right? So original function, first derivative, second derivative, third derivative, fourth derivative. And then since fourth derivative is the same as the original start, 5th, 6th, 7th derivative, 8th derivative, 9, 10, 11. So every fourth derivative, so this is going to be the multiples of 4 are going to loop me back when you have a sine or a cosine. So the reason that's useful is if I know that the multiples of 4 loop me back, instead of differentiating 7 times, which I could do if I really wanted to, I could instead notice that if this is all the multiples of 4, right? So if instead I erase this so that we're clear that there's only 4 items in the loop, right? It's 4 items and I loop back to the top. One way to do is to physically just count, right? First derivative, second, third, fourth loops back to sine. 5th, 6th, 7th would be this, right? So negative cosine of x. The other way to logically think about it is if you know that this is every multiple of 4, then 7 should be right before you hit a multiple of 4, right? So since I know that the 8th one is sine again, it must be just before that. Right? It must be just before sine x in the loop. Well, the one just before sine x, so this is sine x, the one just before it in the loop is negative cosine. Now, the other option is you could have differentiated 7 times, and that's fine. But if I asked you for something like the 29th derivative of a sine function, it's easier to realize that 29 is one more than a multiple of 4. So this is the 28th derivative, so 29 must be a cosine of x. Now, so for me personally, so just if you ever forget this, right, what I will sometimes do is, now admittedly it's a little bit lazy because it just uses S's and C's, but I will sometimes write this on the top of my paper. So down is derive. Later, when we learn how to do the other half of calculus, we're going to learn that up is integrate. So up is called integration, and so if you wanted to go the other direction. But so I've definitely had students that write this, or just write this on the side of their paper to keep in mind that, hey, this is how these derivatives function, okay? Oh, sorry, negative cosine, my bad. Cool, so sine, so if you derive sine, you get cosine. If you derive cosine, you get negative sine. If you derive negative sine, you get negative cosine, and then it loops back to the top, right? So try P8. You can pause me if you want. I'm going to go ahead and walk through it. So if my original function is a cosine, the derivative of cosine, so y prime derivative of cosine is negative sine. And basically it's the same loop, I just started at a different spot, right? My second derivative would be negative cosine. My third derivative would be sine. And the fourth derivative loops back up here. So this, again, is going to loop back. It's a loop that's 4. So any multiple of 4 is going to be right here, which means this must be my fifth derivative. So the fifth derivative must be negative sine of x. And again, you can find that by you could just keep differentiating till you get to 5. Oh, sorry, this wasn't a 7. That was a stupid thing when I miscopied it, so it's 10. So, same argument with the 10, right? If you know that every multiple of 4 is right here, that means that this must be, just like this was 4, it's also got to be 8, right? Like every multiple of 4. So if this is the 8th derivative, 9, 10, the 10th derivative, which is either y10 like this or this expression right here, the 10th derivative has to be negative cosine of x. And again, you could just differentiate 10 times, but in these particular cases, it's a trick question. It's not really worth doing. Okay, let's take it a step harder. All right, so in our E9, I'm going to give you f of x equals x squared cosine of x. And I'm going to ask you to find f double prime of x. We're going to walk through that. And as P9, we're going to do something similar. We'll do an f of x equals, let's do 2x sine of x. And again, I'm going to ask us to find f double prime. Now, one of the things you'll find is that most of the time as we move forward in calculus, it's the function, the first and second derivatives that we use a lot. So although it's important to know how to find like a fifth derivative, you're not going to use it very much. You're going to use the function itself, f of x, the first derivative, f prime of x, and the second derivative, f double prime, most of the time. Occasionally there will be a reason to use a triple prime, but most of the time the functions that we're actually going to be doing stuff with are f prime, and f double prime. Okay, so this is tricky because this is a product rule, right? So my f prime of x, right, this is going to be my u times v, is going to be u, dv is a negative sign, plus v, which is going to be the cosine of x, du, which is going to be a 2x. So already this is super fun, right? My f prime is a negative x squared sine of x plus a 2x cosine of x. Now, if that wasn't already super fun enough, and I did pick the harder version for my problem and a slightly easier one for you, if that wasn't already hard enough, now I have two product rules, because when I want to differentiate, I have a uv here and I have a uv here. So my f double prime, and I'm probably going to run out of room or have to cheat and go this way for a minute, because I think I'm not going to have enough room. So I'm going to deal with this product rule first, right? So u dv plus v du is going to be a negative 2x, right? So that's the first product rule, right? So this is the first of the two products, okay? Plus u dv is going to be a negative sign, plus v, which is cosine, du is a 2. So this was my second product. So if I clean all of this craziness up, and boy am I glad I gave myself some space to work, if I clean all of this craziness up, I seem to have a negative x squared times the cosine of x. These two seem to be like terms, because these both seem to be a negative 2 sine x. So I think I get a negative 2x sine x. I think I get a negative 4x sine x, right? Because those two are like terms, plus a 2 cosine of x. Notice that it's only the x's that are inside the trig functions, right? And that's about as good as it gets. So it's kind of tedious and awful, but that is a product rule where I have to use, where I have to differentiate twice, and so there's a lot of products. So if you want to try and pause me, you can go ahead. I'm going to do P9. It is about the same, slightly easier, just because the product rule is slightly less ugly. So again, I have a product. I'm going to have a u and my v, right? My u is the 2x. You can put the 2 with either function. It's just easier to put it with the x. So my f prime of x is going to be u dv, which is going to be cosine x, plus v, which is sine of x, du is a 2. Here's the reason this one's slightly easier. When I clean this up, I notice that the second expression is, like the second term here, is not a product. So I do have a product here, 2x cosine x, so that's going to have to be my u and my v, But this guy is thankfully not a product. It's just a 2 in front of a sine x. So I don't have to do a product rule there, which is why I mentioned that this one's a slightly easier problem. So my f double prime, I'm going to have to do a product rule. So I'm going to get u dv is going to be a negative sine x plus v du, right? And then I'm just going to differentiate this guy directly, and I'm going to get that that's a 2 cosine of x, right? So if I clean that up, which is going to involve erasing some of this. So if I clean this up, and again, this one was slightly nicer just because you didn't end up with 2 product rules in that second step. I get negative 2x sine of x plus 4 cosine of x. And that's about as nice as it gets. I mean, technically this one does have a GCF of 2 or negative 2 if you want, but it's not pretty. All right, so I'm going to stop this video here, and we'll go ahead and we'll do a little bit more in the last video of this section.